So today's class is Make Something Big. We're going to do large format machining. And this is one of my favorite assignments. It's Make Something Big. So an example is, this was a student, David, who his girlfriend wanted a standing desk and he couldn't find a good one. So here, if we go back, so this is using a large format milling machine, taking a 4x8 sheet of plywood, cutting out a kit of parts, and then assembling it into a standing desk. And then here's the girlfriend with the standing desk. And in fact, that became, he spun that off as a startup, and this became a little business to make those. And another one of those, Vanessa, can you explain this?
Yes, Neil. So this is our project, furniture customization in Peru. We are actually working in this development project. We are actually working in OpenGIS technology. So the idea is to test our furniture, customized by online, and then you can change height, weight, and deep. You can change material. So this is our project in Peru. So we are very happy because we just upload this new upgraded this week. So I really want to you explore and test, and maybe let us feedback, because you have a box to send us a feedback about our project.
Good.
Thank you.
A few other examples of related projects. Open Desk is a series of open designs for furniture. At Fab is another site with examples of these. Let's see, there's a question about cost. Vanessa was listing projected pricing for it. Then some neighboring projects. This was done by Fab Lab colleagues associated with ShopBot, I'll talk about, to make shelter, rapidly make shelter for things like disaster relief. This was a colleague who made, this is the Museum of Modern Art in New York, and this whole house, this beautiful structure was made as a rapid prototyping project, and I'll talk more about that at the end. WikiHouse is a project taking this sort of rapid prototyping on house scales. Barcelona, let's see, this was a Fab house, and this was a Fab lab house as one of the biggest ones. These are all done as large-scale rapid prototyping projects. So details depend on your lab, but you'll get in US units a 4x8 sheet of plywood, and you can make like a desk, a bookcase, something furniture scale. So first, tools. Shaper was spun off from my lab, and they make a really interesting machine where it's a router. You move it by hand and it cuts, but it has a vision system and motors. And so the idea of this one is you do the coarse positioning, and then the vision system does the fine positioning. So unlike all the other tools, you bring your stock to the machine. For this one, you bring the machine to your stock. You can bring it wherever you need to work. So that's Shaper. I'd say the workhorse for this week is ShopBot, a close friend of the lab. He was actually a neurobiologist, Ted, who founded it, and was making machines in his garage, and was more excited about the machines and made that the career. And so these are in the range of $10,000 to $20,000 to make a large format tool. A typical one of these is 4 feet by 8 foot by 1 foot volume. And then with a hefty spindle, I'll talk about materials, but that's a workhorse in many of your labs. Then compared to that, Ansrud makes machines that are $100,000 rather than $10,000. Roughly, the performance is similar. The difference is the Ansrud is much stiffer, so you can machine faster, and it'll last in sustained production much longer. The ShopBot, you periodically need to readjust it. And so those are $100,000 scale production machines. And then beyond that, this is an example of a machining center where these go from 3 to 4 to 5 axes. They're much stiffer. They handle much higher torques, and those go up to hundreds of thousands of dollars. There's a question about the shaper. The shaper really isn't quite enough for this week's assignment. The reason is I want you to do feeds and speeds and fixturing. So I do want you to learn how to use a large format tool. It's really difficult to do this assignment with just the shaper, and the shaper doesn't cover all the skills. You can use the shaper for part of the project, but it doesn't cover all the skills we'll be covering for the week. Let's see, there's a note to Shapeoko. These aren't quite as, let's see, I don't think these get quite as large. These are on the small size of what we would call large format machining. And then Jens in Norway, I'll bring all of these people for the recitation. Jens has been doing really good work on open designs of machines of this size. And so, let's see, let's find the page for the Humphrey. Yeah, the Humphrey is, oh, let's see, Ricardo was saying Shapeoko Pro are, I see, that is a bit larger than I realized. I'll make a note of that. So, okay, I'm muting everyone. Unmute if you want to talk. So this is a large format machine design Jens has made in the Fab Lab that can then make the parts of the machine. So Jens has been doing these beautiful large format machines, and it really is realistic for you to make this machine in your lab. So the focus is on those sort of machine, that class of machine. So then comes the stock. What is the material we're going to use? There's a question. There are questions in the chat of, is that enough? It's not a rigid boundary. The guidance is meter scale. You want to have at least an axis that's on the order of a meter big. And we want something where you need to do fixturing, feeds, and speeds. So there isn't a sharp boundary, but we want it to be meter scale, sort of, order of magnitude person scale for this week. And a good way to answer is the skills I'm going to talk about now. First, cardboard. So you can make furniture out of cardboard. This sort of heavy duty cardboard, the best way to cut it is with a powered knife. But you can actually surprisingly mill heavy duty cardboard like that. Jason is asking about the machine. Jason, you can try to make, so for this week, it's just the mechanical parts. Trying to make a machine, a large format machine would be fine for this week, with the one note that I want you to do design work. So it's not enough just to download Jens's design. You need to do some of the design work. to enhance it, but making parts of a large format machine is fine. It could be, you know, any application you want. So you could make furniture out of heavy duty cardboard. The other note about cardboard is I really recommend for this week prototyping. So you can prototype just in the CAD tool, but if you're going to spend a lot of time machining a really big thing, it can be really handy to laser cut a little cardboard model just to go over the design of it. There's all sorts of things you find when you assemble the small parts that can be hard to do just in the CAD tool. One of the materials you can use is this. Sorry, I missed. So rigid foam insulation. This is used when you build a house for insulation, but this machine's really easily. It doesn't have good structural properties. You can use it to make trim or molding. One of the main uses of this, though, is you can make molds. If you want to cast a large part, you can machine foam to make large molds. Veneer plywood is, for example, what David is using here. This is really nice wood that is sanded with a smooth finish, has a nice grain. If we go back, prices for wood have gone crazy during the pandemic. They've been coming down. They're still higher than they used to be. But if we look at types of plywood, veneer plywood is much more expensive. Oh, I see. They've got this nicely listed. So, you know, a nice sheet of plywood is, you can spend $100 on a hardwood with a nice sanded finish for veneer plywood. Then MDF is, let's see if they list that here. MDF is medium density fiberboard. This is short fibers in a resin matrix. It's much heavier, and it's got much worse structural properties. It handles, it'll crack, it handles lower loads. What's good about it is the surface is very smooth, and it machines really smoothly. And so this is used, for example, in billboards when you put up a sign to have a very smooth backing for it. But it's not a good structural material. Medium density overlay is the best of both worlds. MDO has a plywood core with an MDF surface, so you get a better structural core and a smoother surface. Then we get to OSB. OSB, it is like sort of literally the sausage or hot dog of wood. You know, sausages or hot dogs are made from, you know, bits of meat left over put in a case, and that's literally what OSB is. OSB is bits of wood left over from making other stuff that you smush together and glue together. OSB is the cheapest kind of wood. And actually, this has come down. This had gone up. This is back down to $10 a sheet. I'm glad to see. OSB is used for really crude stuff, like when you board up a building with a broken window. It has a Judy asking about mincemeat rather than sausage. The distinction is sausage gets put in a case. Not that I'm a meat expert. OSB has a bad reputation that's maybe worse than it needs to be. So OSB has a rough surface because it's little smushed together chunks of wood. And so when you get it, it's rough. You can't machine it to high resolution. However, you can sand OSB, and then you can seal OSB. And so you can start with cheap OSB, then sand it, then seal it, and you can end up with a smooth surface. Unlike hardwood plywood that right off the bat has a beautiful surface. So you can improve OSB by sanding, finishing, painting. But the main virtue of OSB is it's just so much cheaper. And so that's the main material for this week. That typically we give you OSB as a starting wood that you can post-process. Later you can go back and you could pick more expensive types of wood. Ricardo's noting OSB used in framing. So its reputation is worse than deserved. You can nicely finish it, and again, it's much cheaper. It's ballpark $10 for a 4x8 sheet of OSB. Some other materials. Valchromat is a kind of fancy MDF. HDPE is a dense polymer that machines easily. These are examples of machines we make out of HDPE. Polycarbonate is a really tough polymer. It's also called bulletproof glass. You can't easily laser cut it, but it machines fairly easily. There's a question about toxics. So for OSB and MDF, what matters is the binder. There are MDFs that used a binder that outgassed hazardous chemicals. And there was a scandal when these were used in the US for a disaster emergency response with trailers that made people sick. But there are what are called green MDFs that uses friendly, low volatility binders. The choice is the type of binder you use for it. I had mentioned Garolite. Good. This is what I was trying to find this in the beginning when I talked about making a box structure. So what Jake is doing here is making a torsion box to make a stiff machine. And he's making it out of Garolite. Garolite is like PCB stock, but it's with a fiber reinforcing, so it's not hazardous to machine it. We'll talk about this when we get to the composite week. And Garolite machines beautifully, has good structural properties. Let's see, Arnie's asking about OSB. OSB usually, it's usually more of a concern for MDF, because in MDF, the matrix is holding it together. In OSB, it's chunks of wood with just a little bit of binder. So I'm less aware of hazards from outgassing from OSB. It's more of an issue because there's just much more resin in MDF compared to OSB. So Garolite machines easily, good structural properties. On a machine like the ShopBot, you can't machine stainless steel. It's not stiff enough, but you can machine aluminum. Jens machines aluminum all the time on his machines. And you can also get these materials that are a really nice hybrid. Highlight is an aluminum skin on a polymer panel. So you can bend it and machines really easily, but gives you a nice metal surface. And again, let's see, OSB for long-term use is fine. It's stable, but again, you need to finish it. So you need to sand it and seal it and paint it. But then it's fine as a structural material. If you go back, these links, this is just a search on finishing OSB, but you'll find lots of articles on how to start with OSB and how to finish it. And so, these are examples of OSB furniture. As long as you finish it, the surface is unfinished. It's rough, and if you rub it, parts will flake off and grind. So as long as you seal it and finish it, you can make long-term things out of it. And once again, the whole point of it is it's about 10 times cheaper than hardwood plywoods. So Garolite is like a friendly composite, and so it's a nice structural material. So those are materials for this week. For vendors, you can buy for example, McMaster Carr list types of Garolite, they list HDPE. You can buy those from a vendor like that. However, materials from here cost much more than from the sources directly. They're kind of a middleman between it. So this is, for example, in the US, a vendor to buy plastic stock directly. This is a vendor to buy metal from. These are very local. So these ones are local to me. These are all metal, these are all wood vendors in the local neighborhood. And one of the things to know about them is those are oriented to, like, somebody is building a whole housing development and needs huge amounts of wood. And then you can buy what's left over. So what they consider scraps, you would consider a complete project. And so it's good to visit them, get to know the local vendors, and find what's left over from big jobs through them. Similarly, I've been showing Home Depot in the US is a home supply vendor. Here they're listing types of wood available near me. But one of the things to know about this is buying wood from a vendor like this is a bit like buying vegetables from the market. There are different vegetables available each day. And so there isn't simply a standard inventory. You know, each time you can go, you can see what vegetables they have, an equivalent, what would they have. Sometimes there's limited stocks, the prices vary. And so don't design the project, then go find the stock, go visit the vendors, learn what they have, and design the project around the stock that's available. So those are vendors. Then come the job shops. So Proto Labs is an example of a job shop that can do every process. In particular, they can do machining. So if you do machining, they can then do production runs. Then there are a few of these that are wrappers around the Shenzhen manufacturing ecosystem. Prices for these have come way down. And then a really interesting one is there are a few of these platforms where this is next door to Fab Labs. This is a network of little workshops with a platform, so you can submit a job and then lots of little workshops can bid on it and do the work. And so this lets you go. So if you design a piece of furniture and want to sell it and you want to go to short run production, you could ramp up capacity locally. But these are types of vendors to do fulfillment for that. Okay, tooling. So this is inventory of standard tooling we send in when we set up a fab lab. Tooling is the tool that goes on your machine. And there's many decisions for this week. So the first decision is a drill versus a mill. A drill comes to a point and has spirals that go around, and it only cuts down. An end mill, and we'll talk about different designs, has flutes. And so the end mill can cut down, but it can also cut on the side. So the first difference is we're using mills, not drills, because the main thing we're going to do is move horizontally to cut. We'll be going vertically to go down, but then we'll be moving horizontally. Routers, so an end mill can take multiple cuts down. Routers don't vary the depth of cut. They have one depth and then you move horizontally. But you can get routers that have all sorts of bit shapes. You can get ones that look like that. You can get ones that make interesting trims. So you can get routers that have all sorts of interesting shapes to shape the edges of cuts. And that's used a lot in woodworking. An important criterion is the flutes. If you look at the bottom of the tool, you'll see the flutes that then spiral around it. And so that's a 2-flute tool. Most common are 2, 3, or 4 flutes. A 2-flute tool has more space to remove chips, but gives you a rougher finish. As you add flutes, you get a smoother finish, but there's less room to remove chips, so you have to machine slower. So typically, you'll start with a coarse cutting tool for a rough cut, and then if you need a nice surface, and we'll see more in mold making, you use a finer flute tool. You can pay a bit more to have the tool with a ceramic coating. So these are typically carbide tools, and with a carbide coating, it makes the tool a little bit more expensive, but it lasts much longer. So typically that's worth doing. If you look at the tip of the tool, right now we're looking at the face of the tool. One kind has teeth that don't meet. One kind has teeth that do meet. This sort of tool can plunge straight down. This sort of tool can't go straight down. It can only machine horizontally. The reason for using this is it has more chip clearing because of that space. But we almost always use, this is called a center cutting tool. We almost use these because you want to use it to go vertically as well as horizontally. Then looking from above, the machine is turning clockwise. And so if you look at the flutes on the side of the tool, they can spiral this way or they can spiral this way. And so if the tool is turning clockwise, this one is lifting up, this one is pushing down. And so the reason that you can get both kinds, those are called upcut or downcut. If this is the surface of the stock, if here's the tool, if you're using an upcut tool, you'll get a slightly rough top surface. On the other hand, if this is the bottom side, an upcut tool will give you a good finish here, whereas a downcut tool will give you a rough surface on the bottom side. But if you use a downcut tool on the top surface, there's nowhere for the chips to go. So you can actually get center cutting tools that have spirals that go one way and the other way. And so you're downcut on the top and upcut on the bottom. A common thing to do is to do a shallow downcut. And then once you're into it, then do the rest with an upcut, because that's better at pulling the chips out. And then I'll also talk about more advanced tool paths. So something you need to decide is upcut, downcut, or you can get tools that do both. And then finally, this is a flat end mill, and it makes flat surfaces. You can get ball end mills that are curved like that. And ball end mills get used in finish cuts. On a flat surface, it's bad because you get a wavy surface. But when you're making a 3D part with curving surfaces, you can get smoother finishes depending on the geometry with the ball end tool. And so we'll talk about ball end tools when we do mold making. So in your stock will be standard choices, but you'll see there's a much wider range of tools. And the first thing you need to do to pick out for this week is the tooling you're going to use. Then the next thing you need to do is what's called speeds and feeds. This is a list to the Machinery's Handbook. It's a Bible of machining. And I recommend you should have this in your shop next to your machines. It's full of good information. chip load is how much the tools bite. So if you think about so we have the end mill with the flutes. If you look at the end of it, we have where the flutes are meeting. And then this is going to cut into the stock, and we're going to move the tool while it's spinning. And so each time the flutes go by, it takes a bite out of the material. And the chip load is how much each of those little bites is as it goes by and cut. And the chip load is the rate you're feeding divided by the revolutions per minute times the number of flutes. And the range is between, in English units, between 1 and 10 thousandths of an inch. If it's below a thousandth, you're not only wasting time, the tool isn't even cutting properly because it's not getting pushed into the material to bite. If it's over 10,000, you're taking so much that the machine will be screaming. You're putting a big load on it. You're getting very rough cuts as you sort of rip the material out. And so there's a happy place in between where it's making a good cut, you're making good progress, but you're not overloading the tool. So that's the chip load. Then there's the cut depth. So if you need to cut through a thick piece of stock, you do it by making multiple passes. And a good rule of thumb is if this is our end mill, this is the end view, the distance between passes down is on the order of the diameter of the tool. So you go down vertically, roughly as wide as the tool is horizontally, is a good rule of thumb. And then step over is, if you're just cutting an outline, you make one pass. But if you want to make, for example, a flat surface, you need to do multiple machining passes. If you make the machining passes right next to each other, you get a little ridge in between. And so step over is how much you overlap the tools. And we'll see more of this in mold making, but typically half of the diameter is a common step over. Gideon's asking about how the chip load relates to the type of material. So the feed rate is separate from the chip load. So the feed rate is how fast you move into the material. Well, actually, no, these are all connected. On a harder material, you want to feed more slowly and have a smaller chip load. And one more parameter is, depending on your machine, a more advanced machine lets you pick the revolutions per minute. So all of those parameters of chip load, feed rate, and RPM depend on the material. And that's where a reference like this comes in. Your lab will have rules of thumb you use, but books like this exist to have tables of exactly all these parameters for the material. You can vary these parameters to find where it's happiest, but your lab will have tables of them, and there's reference tables of them. Lubricants do two things. Lubricants help lubricate the cutting, and they help remove the heat. You won't need them for wood, and increasingly, when I talk about tool paths, I'll talk about how they're not even used for metal machining. It depends, but there's reasons to avoid them, which I'll talk about. Abrasive machining is an interesting process where you use an abrasive slurry. So you can't machine glass, but what you can do is, if you take a tool with no flutes, just like the back of an end mill, and then you put an abrasive slurry and spin the slurry, it grinds in and actually lets you machine a hard material. You have to do this very carefully because if the abrasive slurry gets into the bearings of your machines, it'll destroy them. So you have to confine the slurry, but you can do abrasive machining to machine hard materials. And grinding is a very specialized kind of machining. These are machines that look like milling machines, but they numerically move grinding tools. And in particular, this is how all these other tools get made. So end mills, can be beautiful. I think they're beautiful, all of these shapes. And typically those get made by numerically controlled grinding processes. Next up, fixturing is a big subject. So you need to hold the material. You can hold it for smaller things in a vise. So this looks like an ordinary vise you use to hold something on a workbench, but this workbench costs $600, not $60, because the surfaces are to very high tolerances, completely flat and rigid. And so this holds your stock square in the machine, and you can, for example, flip it and rotate it and everything lines up. So these are like bench vises, but much higher resolution for machining. You can fixture with bar clamps. So bar clamps are just clamps you slide on to hold your stock. These work well for small jobs. The issue with a bar clamp is if this is your machine, if this is your stock, and I'll talk about underlays in a minute, the bar clamp is holding it on the sides, but nothing is holding it on the middle. So if you start machining in the middle, it's going to be, your whole stock will be bowing and lifting and moving. And so bar clamps work for smaller jobs, but they don't work for a big job where you need to hold down in the middle. The workhorse for this is, there's a stack up of, there's the bed of the machine. There might be one layer, and on this layer, you do a machining job where you machine the whole thing. And what that's doing is the bed might be slightly angled compared to the gantry of the machine. So you machine a layer so it's flat in what the machine thinks is flat to make it square. Then we have a sacrificial layer, and this gets replaced periodically. And then we have your stock. And so you machine through your stock into the sacrificial layer. This gets cut up over time, and periodically you replace it. So one of the best ways to do fixturing is to just get a cordless drill as a screwdriver and just put little wood screws in. So you pop in wood screws, and those let you distribute the hold down over the stock. Obviously, you don't want to mill over the wood screws, so you need to place them where you're not going to mill. But that's a nice way to do distributed hold down. You can get special nails for this that are designed for this purpose, and these are polymer ones, so it doesn't hurt if the milling hits them. It's a polymer nail, and you can pop them in with a nail gun or a driven screwdriver, and so those are forgiving. When we get to machining wax to make molds, one of the ways we hold down is just with hot glue. You can make a bead of hot glue, and you can crack it off. For light machining, you can use double stick carpet tape. And for 5-axis machining, where you need to machine all the sides of a part, one of the techniques is you take your stock and then you cast it, for example, a high temperature metal in a low temp metal, you do all of your machining, and then you melt away the encapsulation. So fixturing is a non-trivial task for this week's assignment. Then I mentioned you're going to have a sacrificial layer, and you want to machine that to decide to make the base. And then if we look at a machine like a ShopBot, it has rails going that way. Then there's a gantry going this way. And then there's a z-axis going this way. So we have this axis, we have that axis, and then we have this axis. In a machine like the Ansrud, these are heavy casting. And so just the machine itself is square and rigid. But in a machine like the ShopBot, it's bolted together, and those can all walk. So one of the things you need to do is you need to square the machine. You need to adjust all of these so that the machine is square. And for a less stiff machine, you loosen and tighten bolts. And so the main way you do this is if you do a test cut and you cut out a square, you check to see, is the square a trapezoid? Is it a shear? You check the shape of a cut, and you use that to adjust the machine. And if you haven't done that periodically in the lab, it's an important thing to do to just check that the machine is square. Dust collection. So by the way, when I use Amazon, I'm not particularly recommending buying from Amazon, which is a non-trivial subject. It's just a convenient source to find illustration examples. So this is a dust collector. When you machine wood, you're producing lots of fine dust. It's not seriously toxic, but it's not good to breathe. And it'll cover your lab, it'll get into the computer, so it'll get everywhere. So you don't want the dust to leave the machining process. So a tool like this sucks up the dust and goes in the machine. And a good rule of thumb is if there's a layer of dust around your large format machine, something is going wrong. It shouldn't be escaping the machine. It should be going into the dust collector. So these are flexures. We saw this in laser cutting. This is Vladimir in Moscow. If you machine a series of beams like that, you can start with a rigid flat sheet of wood, and you can make it so it can bend. And it can be very anisotropic. So it bends in one direction, but it's stiff in another direction. Then this is a really nice technique. Upper left, this is called kerfing, where what you do is if you have nice plywood that has a continuous top surface, this doesn't work as well in OSB. If you don't machine all the way through, you get ribs that then let you bend it so that you have a smooth curving top surface from what started as a rigid piece of wood. So those are flexures, kerfing, living hinges. Then you can steam wood and bend it. If you heat it in a steam box, it softens the wood, then you bend it, and then it cools off. So you can bend it into shapes. And then there's wood designed for steam bending, where plywoods, you alternate the direction of the plies. If you know you want to bend it, this orients the ply so that it's not quite as good structurally, but it's designed for bending. You can use fasteners to bolt things together. You can use wood glue to glue things together. But a good rule of thumb is to try to avoid that. you can design in wood to avoid the need for fasteners. And this goes back to the joints from the laser cutting week. And what's nice is that makes the whole structure disassemblable. So you can take it apart later, you can edit, you can modify it. A big subject is joinery. So joinery is, it gets a fancy name because it's how you join wood pieces. So this is a lovely project that came out of the Kamakura Fab Lab. Kamakura Fab Lab. The Kamakura Fab Lab is in what was a ancient sake brewery, and it's full of beautiful joints. So each of these is a different way to join 1, 2, or 3 axes at intermediate or corners based on what you can see, what you can't see, where the loads are. There's a need for every one of these types of joints. And so this was this beautiful study of traditional Japanese wood joinery, of all the different types of joints that are used to hold things together. Some neighboring concept. This is an article on reciprocal frame construction, where you link elements to make these beautiful space-filling structures. So that's reciprocal frame construction. Tensegrity is a beautiful thing that dates back to Buckminster Fuller, where fibers are good in tension but bend easily. Beams that are stiff in flexion can be connected. So in a tensegrity structure, if you look at the structure, none of the beams touch. They're connected by the tendons. And tensegrity divides labor so that the beams handle flexion and the fibers handle tension. And it lets you make these beautiful structures. There never really have been any great applications for it. So it's never really found a killer application that needs it, but it's a beautiful kind of structural system. And then this is a link to, this is the oldest reference. I've shown you a lot of references that come from moments ago. This is the oldest reference in the class. This is to a paper written in 1869, beautifully written, lovely. Yeah, no, Frank, the biosphere in Montreal isn't tensegrity, it's geodesic. That's also from Buckminster Fuller, but it's not tensegrity, it's geodesic. This paper from 1869 from Maxwell, who gave us Maxwell's equations for electromagnetism, is on structures. And in it, what he clarifies is the relationship between the number of degrees of freedom and the number of constraints. And so a good example is if I take vertical beams, I connect them to horizontal beams, and I want to make that a bookcase. This will be a terrible bookcase because it can shear. Nothing prevents it from shearing. It's a mechanism and can easily move like that. On the other hand, if you take the bookcase and if you just run tendons that way, if you just have thin beams or string, something that way, this adds constraints. And so this can no longer shear. And so you need, what Maxwell clarified is you need to count how many degrees of freedom there are in the structure and how many constraints. If it's under constrained, it's floppy. If it's over constrained, you're wasting material on excessive constraints to hold it. And right at the boundary, you're between under constrained and over constrained. Let's see, Aristarco, you're showing an example of that?
No. I was saying that.
Oh, no, this was about kerfing. Yeah.
Yeah.
So kerfing is noting the orientation. That you want the fibers you want the fibers going this way in the kerf, not this way in the kerf. You want them perpendicular to the kerfing direction.
Yeah, that's right.
Yeah. Okay. And let's see, there's a link to a tensegrity project. Okay. Okay, so those are some insights into structural design. Now comes a big subject, which is toolpaths. When we machine circuit boards, I'm going to give you, sorry, I'm going to mute for just a minute. I'll be right back. Sorry, I'm having some work done in the house. Oh, let's see. Ricardo is noting about, yeah, run out. Run out is going to matter more when we get to mold making. Run out is, if this is your tool diameter, in theory, that's the size of the hole you make. But in practice, the tool might be at a slight angle, the bearings might be slightly wearing. And so instead of staying at a point, the tool can wander a bit and the actual cut is bigger than what you thought. And we're going to worry more about that when we get to mold making. Okay, so, oh, sorry, I've got it right here. Kerf is, if this is the stock, if this is the tool, kerf is what's left as it goes past. Offsetting is, if you want the stock to end here, you need to move the tool over to here. And then run out is, the kerf might actually be bigger than the tool because the tool wanders a bit. So to make the tool for this week, we need to account for the kerf. Then you need to pick the type of tool path. If here's our tool spinning this way, we could cut in that direction or in that direction. In this direction, it's biting by climbing in here. And so that's called climb machining. In this direction, it's biting in down below here. That's called conventional machining. Conventional machining drives the tool into your stock. And so it helps hold the tool in place. But it bites in down here where it's hard to get started. And leaves a rougher surface. Here, this bites away from the finished surface and then cleanly leaves it at the end. So climb gives you a smoother surface, but it puts much more force on the machine. And so typically climb for finish cuts, conventional for rough cuts. This was just a little image from mold making. You rough cut with horizontal layers. And that's probably all you're going to do this week. And then you do move all the axes to do finish cuts. And we'll see that in mold making. A really interesting subject is the emergence of all kinds of high-speed machining, what's broadly called high-speed machining. So one reason to not use lubrication is the tool keeps getting hot and cold and hot and cold. It can be better to just let the tool run hot, and that's dry machining. Then there's a whole series of techniques where, because the end mill cuts better on the side than the bottom, instead of plunging straight down, if you plunge at an angle as a ramp, it cuts more effectively. So that's ramping. Normal in traditional machining, you just cut down in layers. That's the obvious thing, but you've got the whole side of the tool. So an adaptive clearing is you plunge down or ramp down, get the tool pretty far down, and then you work your way back up. And that uses more of the side of the tool. Adaptive clearing, rest machining is you start with a big tool and then go back with a little tool and just get the few bits that are left. Swarf machining is where you tilt the tool to follow the surface. Trochoidal is a beautiful kind of machining that when you first see it looks sort of crazy. In trochoidal milling, let's see, let me see if there's a good video. In trochoidal milling, it looks like, okay, good. This is what I want to show you. It looks like the tool is going crazy. So, okay, so right now, let's see. Let me get to where it was doing it. Okay, so that's trochoidal milling. What it's doing is, climb machining makes a chip that starts thick and ends skinny. Conventional makes a chip that starts skinny and thick. What trochoidal milling does is runs the milling machine in loops like that. And what that's doing is it's giving you chips that are roughly constant cross section. And so trochoidal milling lets you make smoother surfaces with faster machining by spinning around. It's a little bit like an orbital sander. It's spinning in loops. And so that's trochoidal milling. For this week, you'll be milling on one side. For some machining, you need to register, flip, and do both sides. 2D machining is you just plunge and cut. 2.5D is you cut in layers. 3-axis machining is where you move all of the sides at the same time. Once you're doing that, you need to account for the length of the tool. Then a lot of, let's see, this we'll worry about in mold making, about how deep you can cut. For this week, we do need to worry about these issues. So let's see, let me start a new one. T-boning is, if you machine a slot like that, it's actually going to be curved here. And so if you want to fit a part in there, it'll hit that. So what you do is you make something that looks like that, or something that looks like that. And so by going slightly over, a part can fit in here, and you account for the curvature. Let's say this is your sheet of stock, and these are some parts you're cutting out. As you get near the end of the cut, nothing is holding the part, and it can start vibrating away unless you've got a nail holding it down. So one of the things you can do is, let's see, from the top, you can have your part, and then you can have skinny little tabs that hold it in place. And so there's something holding it in place, and you just snap them off. Onion skinning is, rather than machining to the bottom, you leave a very thin skin here, just enough to hold your, just a little bit there to hold your part in place. And when you're done, you can just pop that out and trim it off. And so those hold your stock in place. Nesting is, this is software for nesting. Once you design your thing, you need to space them on the stock. And the better you pack them, the more efficient use you make of it. And so you can do it by eye, and there's software to help you nest to fit your stock. Then, especially at the beginning, you're almost guaranteed to get wrong things like the depth of cut or the direction of cut. So a very common thing is, here's your stock you're going to cut. You get your tool zeroed. So you put your tool there ready to machine. But it turns out the machine is set wrong and it thinks 0 is here and it plunges into your stock, and bad stuff that I'll talk about can happen. Or another example is just, looking from above, here's your stock, and you put it here, but the machine thinks it's over there. And so cutting error is get your job set up, get everything ready. But if this is your stock, move the tool up here so it's not touching anything, and start doing your cutting in the air. Make sure it's doing the right thing, then go back and lower it down. Another good thing is don't do the whole job right away. If this is your stock, go to a corner, make a little slot, or cut out a little square. Just do little test cuts to make sure speeds and feeds are all working properly. Let's see. There's a link in the chat to okay, bending plywood in a structural system. Depending on the CAM software, it can simulate the process. And again, I suggested making small prototypes before you do the big job. So for software, CAM turns your job into the toolpath. So for example, vCarve is one of the tools that comes with ShopBot to do path planning for it. This is commercial CAM software. It's really an AI problem. You're trying to take the brains of a machinist and put it in a software. FreeCAD has a path planning module. I know this exists. I haven't tried using it. One of the strengths of Fusion is Fusion has very nice, very powerful CAM built into it. SolidWorks has CAM. Fusion's CAM is in particular very tightly integrated. And then mods, which I originally wrote and is forked into a community project, can do not advanced toolpaths yet. It could be added. But this is an example of, I've loaded in a shape, and then here's all the machining parameters, and then it just generated that, and that's ready for machining. And so mods will let you easily make simple tool paths. It doesn't yet do the more advanced machining operations. If you really get ambitious, the formats the machines uses are easy to write. And so if you're doing something algorithmic and like programming, you can actually write these toolpaths directly. Of course, you want to simulate it first before it gets to the machine. Okay, safety. This is the most serious week for safety. This is a horrible story about a student at Yale who died in a machine shop. She was using a lathe. Her hair was loose. Her hair got caught in the lathe and she died. When I was in grad school, I was working in the machine shop late at night. A fellow student literally looked up and said, "I'm bored," and looked away. It ran through his finger and cut his finger off. Luckily we were there and could run him to the hospital. These tools can seriously hurt you, and you can also hurt them. So this first link is to just, this is a training link for the MIT students. You're going to go through safety training, and the safety training is very serious for this week. So you can get splinters from the wood. The chips you're making are sharp. They can cut you. They're hot. They can burn you. Things can come flying out of the machine into you. And this was an example of, in this class, at this nice Fab Lab, if you look, you'll see that line there. This was an example of the depth and the location of the cut origin was set wrong. So they started the job and it went plowing into the machine. They thought everything was fine. They went on with their work. And then the fire department came. So what had happened was they have their stock. The tool had plunged into it really fast, really deep. The dust collector had sucked the chips out and brought them into the dust collector. The dust collector has a fan pulling in, and then you've got the chips in here. These were so hot, they were glowing. They got into here, and now they're in a place that has easily flammable material with active airflow, and the hot little embers ignited inside the dust collector. And once you have a fire in a dust collector, you can't do much more than call the fire department. You can't easily put it out. And so it ignited. Here's the sort of the back action of the fire coming out through the dust collector back into the machine from the fire that was ignited from the chips from the machining. And so that was a great example of the need to cut air before your machine. When we machine with circuit boards with tiny little end mills, you'll break them if you do something wrong and will be unhappy, but no more than that. These bigger tools, if they break, hot, sharp chips come flying out, and it's very hazardous. So you should never, ever break nothing. If you do everything right, there's no way to break these tools. If bad things happen, you can break them. So that's why when you're doing large format machining, you have to wear safety glasses, not just eyeglasses. You need to protect your eyes against a projectile. You wear substantial shoes for things that can land on you. You want clothes with nothing loose, certainly no loose hair. You want that tied up. Handling the wood, I would wear gloves. You want to use good protection, just personal protection equipment. You want to look, listen, and smell. So you want to look for things that are not right. A really good index is listen to the machine. When it's machining properly, it makes a happy sound. When something's going wrong, it screams. If the machine sounds like it's in pain, it probably is. Once you start getting in a limit where you're making glowing embers, you can actually smell what's going wrong. You never, ever, ever, ever reach into a powered tool. And there are a lot of injuries from that. So let's say, here's your piece of stock. Here's a piece you're cutting out. Here's the end mill coming in. It's almost done, but now it's starting to vibrate. So you might be tempted to reach in and hold it, or it's starting to spin. What happens then is, for example, if this binds on the tool, it can start whipping around at the speed of the tool while you're holding it and slice off fingers. So you never reach in while the tool is powered, just absolutely never. These tools always have an emergency stop. It sounds obvious, but before you turn it on, make sure you know how to turn it off. So before you turn it on, just stop and think, if something goes wrong, how do I stop it? And you never do this alone. You always want to have people in the vicinity, and that's both as a check to make sure you check each other. But if an accident happens, you always want somebody there to help. And you don't do this when you're mad. You don't do it when you're sleepy. When you don't do it when you're rushing for time. You need to be in a Zen-like state. You need to be one with the machine. Don't do this when you're not in a good state to machine. Done right, nothing ever happens. But these are all the ways why safety is serious. So on the one hand, I'm trying to scare you. On the other hand, most people doing this never have an accident. The accidents come from mistakes. And so early on, when we talked about Git, I noted you'll make mistakes, and we talked about the mistakes. You don't get to make mistakes this week. And so you'll go through the safety training, you'll help supervise each other to be able to work safely. So do your lab safety training. As a group, test your machine. Check the runout. How does the curve relate to tool diameter? Check alignment. If you make a square, is it a square? Go over how you fixture. What are the speeds and feeds for your materials? And what are the preferences in your shop for toolpath production? Then make, and by make, I mean design, mill, and assemble something big. This is a link to this lovely project was done by a colleague at MIT, where he made a shotgun shack for the Museum of Modern Art. And the whole thing was made on a ShopBot and assembled with a rubber mallet. And so this whole house is just pieces snapped together to make a whole house. That you don't have to make a house for this week. Let's see. Ricardo is noting, yeah, gloves to handle wood, not for running the machine. So make something meter scale, and furniture is a great example for this week. At the end of the week, you should feel liberated that you can make things on the scale of the environment around you. Extra credit is avoid the need for fasteners or glue and design joint systems. And other kind of extra credit is don't just make flat pieces, but play with flexures and curves to make something with curvature. You don't need to do it, but those are interesting design challenges for the week. You're going to be limited by machine time. So you can't do this assignment just before class. Get the design work done early and leave plenty of time to get in the shop for the machining. Okay. So that's large format machining. Then, wrong tab, we want to be here. We do have a recitation on Monday, and this is getting ready for next week on what to do when your electronics doesn't work. And then as a reminder, if we go into the class issues, once again, make more use of the issue tracker for questions, offers, but a reminder that US is going to be changing to daylight savings time. We're going to stay linked to the Boston schedule. And so keep an eye on this over the next few weeks as some parts of the world change later, some parts never change, but we'll stay locked to 9 o'clock in Boston. Okay. Final questions or comments? This is one of the most expressive weeks and one of the most empowering weeks. You should end with feeling you can create the environment around you. But this is one of the most substantial hands-on in the shop week. And so it's a very important week to make good use of time, so everybody has plenty of time, machining time. Okay. Happy large format machining. I look forward to seeing what you do next week. And as always, don't forget Saturday open time. Okay. Bye-bye.
Thank you. Bye-bye.
Hey.
Hello.
Hasta luego.
Bye.